Am I audible?
Yes, you are audible.
So let's start with the week 9. Last time we were studying about the lookup tables. Like, what are the lookup tables? We all know that lookup table is basically the representation of the value function in a tabular form. Like, suppose I have a state S, it is going to state S dash, what action it should perform. So I have A1, A2, A3, number of actions. So which is the optimal action if if I'm in the state S, I'll maintain this lookup table for that. Let us take an example of an MDP only. Or I have a battery of an IoT device. I don't know why it's creating a problem. Okay, I have a battery of IoT device, suppose X, IoT device 1, of 2 as IoT device 1, 2 as Y, and so let it be like I have X and Y state as a tuple. Now, what action should I perform so that it should be energy efficient? Energy efficient means my battery should be reduced as less as possible. With what transmission power? Suppose I have this device and I want to send the data to the server, suppose. Now, with what transmission power should I send this data to the server? This is the client basically, so that less battery is consumed. You got the problem?
What transformation power means? What are we sending? What data means? What we are sending to the server? Data means
anything like any data. Suppose in ML also. What is ML? That like we have a client and we are sending some data to the server. Or if we talk about FL means federated learning. In FL, we are not sending the data, we are sending some parameters. So suppose I take some data, if there is a client is IoT device, and suppose I have number of IoT devices which are sending to the server. Okay. Now this with what transmission power, which means with what power they should send, so that my less and less battery should be consumed, so that it should be energy efficient.
Okay, 1 minute. Just let me ask one thing, that when we are sending some data to an through the IoT device, we need at least some minimum power, because there should be some input volt, means we cannot go beyond below that. So now you are means then why are you optimizing this? So you will choose the below threshold always, right? Isn't it?
No. We have a threshold power. Suppose like this is a threshold power, but there are some other parameters also. Like I have to suppose consider time also. Like time should also be minimized when I'm sending the client, and like client is sending to the data to the server. At the same time, suppose the energy, the battery should also be reduced. This is just an example which I am saying you. Like with what transmission power I should send, so that my time is also reduced as well as my battery is also reduced. So I
Mm-hmm.
should have lesser like so much of transmission. I should have some optimal transmission power so that my time shouldn't be that much of high in order to reduce the battery, or my battery shouldn't be so much of consumed in order to reduce the time. As I am taking that energy and time, they are inversely proportional, suppose, in
Okay.
this case. So
Okay.
now in that case, what is my optimal transmission power? This is just an RL problem, which I like MDP framework problem, which I am giving you here. The state
Okay,
is,
so it is like transportation, right? Means there might be means there are several choice in which route should we transport, means which route should we choose, means I mean
yes, yes,
there are
it can
several
be.
possible power itself the route. You understand my
Uh,
point? That
yes,
several
yes,
possible power is the route, and
yes.
we will choose the route which will means optimize it, means like this.
That can also be the case. The which route is optimal one, so that we can like reach to that base station, we can say.
Mhm, mhm.
Here I am saying with what power I should send so that I can reach the server with an optimal battery as well as lesser time. I'm saying. So we can have many examples like that. Here the state is battery of an IoT device. If I'm taking the like, because my battery will be changed, like suppose it's X, then it will be X dash. My action performed will be the transmission power. And now suppose randomness here, as let us take it as a stochastic nature, stochastic behavior. So let us take it as a randomness as a bandwidth here. Bandwidth is basically changing. So this is a total framework which we can say. Now talking about a lookup table here. Talking about lookup table here, I'll have a second. I don't know why these lines are building up. Wait a second. If I am in a particular state, which means if I'm in X battery level, then with what transmission power I should send? What action should I perform? This is my lookup table here. And as you told me in the last class also, what is the limitation of a lookup table?
That is the means efficient. I mean, it is hard for computation, expensive computationally.
Yeah, computationally intensive, or we can say a lot of memory is consumed, or computationally intensive. Second limitation is continuous states. It becomes difficult when we deal with the continuous states in the lookup table to store all the combinations of inputs and outputs for that. Now let us have an instance when we have a large amount of battery. Oh, sorry, large amount of memory here. And let us suppose these lines are getting built up. Memory is not an issue. Suppose
But due to continuous variable, how many? It is not discrete, so our search space is infinite, right? How can we?
that is why what I am saying, it is difficult. It is difficult to
Hmm,
have a lookup table when we have a continuous state. If I
right.
have a discrete, then it is okay. But if I'm
Hmm,
having a continuous states, it's very difficult. And the
very
second
difficult.
point is the memory. Yes, it is computational. Now suppose that it is computation, like I have a lot of memory in my like a device, and I'm not worried about the memory. And the second thing is, suppose I'm having discrete state, suppose in my problem, and continuous state is also not an issue. what else can be the issue if I have a discrete state and lot of memory?
Sorry, ask once again, please.
I'm saying, suppose like in MDP, we have issue of that it is computationally intensive. Suppose we have a lot of memory. There is no issue of computationally intensive. We have that storage for store all the states in the lookup, lookup table. We have that storage thing. Second thing is it is not having continuous states as well. It is having discrete states. Now these first and second points got cut off. Now the problem is not computational intensive one. The problem is not the continuous state. Now what else can be the issue?
For so many combinations. No, that will not be a problem because you have cut off these two things. I don't know.
You are close enough. Suppose I have a table. Unless I have visited the state often enough, I'll write this line and explain it. I don't have an estimate for the value function. Suppose I have millions of states. If I have a lookup table also, I have to visit for a lookup table also, I have to visit that particular state also. Like if I have millions of state also, I have to visit that state multiple of times so that I can say what is the estimate of the value function, what action should it perform.
Yes.
So it is a tedious task, as you only said that there are various combinations of states. So it is difficult. Am I right?
Yes, because we cannot figure out value function until and unless we are visiting all the states multiple times. That is true.
Yes, yes. In the last class only, we have discussed about the function. I am revising that only. I don't know what has happened to this pen. Instead of representing value function as a lookup table, we try to represent it some kind of parameterized function. So we thought, okay, we'll not represent it as a lookup table, but if we talk about lookup table, it is also it itself is a parameterized representation. So we thought, okay, let us represent it as a some kind of parameterized function. So if we talk about the neural networks, the parameters, there are the weights of the neural networks like that. I think you might have studied in the ML course also about that. But the parameterized representation, if we are thinking to represent it in the parameterized representation, it comes up with some cost. Any idea? Okay. Suppose I am making parameterized representation complex, very complex. So that it can represent any value function without any loss. then what will happen? If I'm representing the parameterized, like if I'm having that parameterized representation complex enough that it can represent any value function without any loss, I can say that the number of parameters is same as of number of states in lookup table. Then what is the use? There's no use. If I'm having a parameterized representation, and if I'm making it very complex as that all the value functions should be represented by this parameterized representation. And because of this complex, I'm doing it complex so that my number of parameters should be same as the number of states in the lookup table. Like it should represent every value function. Like obviously, if it will represent every value function, then the number of parameters would be same as of the lookup table, the number of states in the lookup table. Then it's of no use here. It will have the same it will also be same computationally expensive. It will also have like consume so much of memory. So here we shouldn't make it so much of complex here. You have to accept approximation. You shouldn't go that every value function should be represented by this parameterized representation. You have to accept this approximation. You can't model every value function here. Sorry. Because if you try to model every value function, then there is no use of parameter. Sorry for the interruption. V pi is represented as V hat semicolon theta. Whenever we are writing here, it is a set of parameters. And here, before semicolon is the arguments here. Basically, this is the true value function. And it is approximated by V hat of theta, which is theta is the set of parameters. Now, the question arises, what should be the criteria on deciding what V hat should be? What approximated value function should be? What should be the criteria? The question arises. Now, we'll proceed in the two stages here. First stage. What has happened to this pencil? How output is going to depend on theta, the parameters. Like if we talk about the neural networks, parameters, there are the weights here. These are the weights. Now, how W will define this V hat of S basically? How the parameters will define this like estimate of value function? We can this is just an example, like neural networks, we are taking the weights and how W basically define what V hat of S is. Or we can represent by the regression tree as well to to represent the value function here. Or we can think of the function approximator with the linear parameterization. We'll discuss in more detail in few minutes about linear parameterization. I can give you a glimpse of it. What is linear parameterization? You might have heard about it also before, that it is just, I can say, that it is a relationship between, if I talk about what is linear parameterization, not in the context of RL, just talking about what is it. It is a relationship between representing linear equations with adjustable parameters. Or you can say like representation, or I can say relationship between inputs and outputs to design the controller that adjusts the system behavior. Where were we? This was just a linear parameterization, like it is a relationship between input and output, or you can say linear relationship between, and we talked about how output, now the first stage we were at. Let's go back again. How output is going to depend on theta. Basically, what we are saying is, like, suppose in neural networks, we have weights, how that weights are defining what an estimate of V should be. And the second stage is error measure. Or I can say how I define theta, my parameters, so that I can minimize the error. If I talk about what is error measure, this is what I'm talking about. What is the performance measure? That is the error measure I'm taking. If I talk about what basically is error measure, I can say in simple language, how far is my true value from the estimate value? It will tell me. Or how close is true value from the estimate value? It will tell me. And one main thing is that the error measure shouldn't depend, or it need not depend on the choice of parameters. This is an important point, that whatever the error measure we are taking, it shouldn't depend on the choice, what parameters we have taken. It should be independent of that. Why? So that as it is important for us to compare function approximators, I can say on fair and constant or consistent basis. If it will depend on theta, if it will depend on like fair, like this function approximators will depend upon the parameters, then we can't say, then there will be a biasness in choosing the functional approximators. So that is why it one thing is that it need not depend on the choice of the parameters. If we are comparing the function approximator, it should be like chosen on the fair and consistent basis, regardless of specific parameterization used here. And I can say it shouldn't be influenced by the choice of parameters. So in short, whatever the error measure I'm taking, it shouldn't depend on the parameters, as it should be independent of the choice of the parameters, so that while comparing the function approximators, there shouldn't be any biasness in that. So what we have done till now, the three things. First, while having the function approximator, find the family of the function which I'm using, that we have to consider. Example, like which is the family, neural network, decision tree, etc. Second is figure out what is the error measure you have to use. As I told you, what is error measure? It will tell me the difference between, or how close my true value and estimate values are, which will not depend on the parameters. And the third is how I'm going to find theta that is going to give me good approximation. If we talk about the error measure, you might have heard in the MNET classes as well about the mean square error. What is mean square error? It is 1 by n summation of this, the estimated value and the true value, difference between them, square, mean and square. And the term is actually multiplied by 1 by n. Why it is multiplied by 1 by n when we talk about mean square error? So that basically equal weightage is given to all of the states, we can say, or to all of the weightage is given to all of them. if we talk about RL thing, in RL, instead of using 1 by n, instead of giving equal weightage to all of the states, let us give the more weightage to the or the lesser weightage depending upon the states. I'll tell you just in a minute what is d pi. Talking about d pi of s, here is steady state distribution under policy pi. What is steady state? I'll give you an example also. Basically, from the policy pi, I'll have this NDP trajectory. Or I can say it will go to a Markov chain only. I'm having this Markov chain only. And as t tends to infinity, I'll have the Markov chain and I'll tell you. I stop the Markov chain running and sample the state. The probability that I will find that is d pi of s. What do you mean by now steady state distribution? And what do you mean by this statement as t tends to infinity? I stop the Markov chain running and sample the state. The probability that I'll get is d pi of s. There are a lot of questions when we read this line. So let us have an example. Okay, where were we? So let us have an example of a Markov chain. If I am in the state 1, I go to the state 2. Okay, let us take a CSM example in the network. Where were we? Like I was telling you that now we have AP or client. Now suppose if I have two nodes and AP transmits here. Though I am going to this network side, but let us take it as a Markov chain only. Now I'm having the two nodes and I'm going to this like AP is transmitting. I go to three nodes, AP, C1 and C2, like AP, client 1 and client 2 with the probability 1/2. Now suppose again I say that AP transmits with AP, C1, C2, client 1, client 2. I say that AP transmit again to C3. I'll have no. Now this time I'll have the probability as now what is the steady state distribution here? I have to calculate for pi 1, pi 2, pi 3. What does it mean that I already told you that we have time average as well as ensemble average. If we talk about the Markov chain, we are having two types of averaging, time average and ensemble average. If I talk about time average, which means that like we are going from here to here, here to here infinitely, like many number of times when we are going, we like time 1, time 2, time 3 and averaging it. This is basically the time average. And talking about the ensemble averages, if I talk about the state 1, I am in the state 1. I'll run this Markov chain multiple of times. Like first time I run it, second time I run it, third time I run it, and multiple of times, like many times if I'll run it, then the probability of being in state 1, that is basically my ensemble average, or I can say that is my steady state distribution here. How many times, if I talk about this discrete Markov chain, what is it saying me? I'm going from like suppose 1 to 2, 2 to 3, 3 to 4. Suppose like this is only the Markov chain. Let's not go ahead. Now, the number of times in discrete time Markov chain, the number of times I'll visit this one, the number of slots, like for first iteration, suppose. First iteration, time step 1, time step 2, time step 3, 4, 5, 6. In 6 time steps, I reached one at two times basically. So basically it is 2/6. If I talk about the pi steady state distribution, I'll do it multiple of times, and the number of times I'll stay in a particular state, that is basically my steady state distribution. This was just an example, just to show you what is that, and it will become maybe we'll discuss in future in more detail about it. I hope so that you know about these concepts about time average and ensemble average, as I have discussed in my previous lectures. Here, what I'm taking is after so many of decisions, after repeating it multiple of times, means when I'll get this steady state, when I don't have any more decisions to make. Or I can say now my pi is fixed here. Then I will say that this is basically the steady state distribution for me. Then I can basically find out, I'm sorry, then I can say that I can find out the steady state distribution and the policy pi when I don't have any decisions to make, and the times it will land or it will stay in the particular state. Through that, we'll calculate this pi value or d pi value. So, and the next thing, if I'm trying to find using sampling, which kind of sampling they use, we know that there are on policy, off policy. On policy, which is from the same pi, and the off policy from the other policy which we are referring to. As we have discussed before, here we use this on policy sampling. Summation of t is equal to time series estimated minus the true value. But the main problem here is I don't know my target here. What is the target? The B pi of t. I don't know how we'll calculate this error measure. If I don't know the target, that is V pi of ST. Basically, we should have the estimate of it. What should be the V pi of ST? Like I have an estimation, I have a target. If I'm comparing the estimate with the target and I don't know what is target, then there is a huge issue. How I'll compare my estimate with the target? Let us go more about it. Classical regression technique. In classical regression, if I talk about ML, we have a data set here. And from the data set, what we are doing it, we are learning from the data set and we are finding the estimate. That is what is happening. If we talk about RL, what we have, the state, then what we are doing, performing an action, then the reward is coming, then we are going to the next state, action is performed, again the reward is coming, and so on. We have a trajectory here. Instead of this, we can say the data set, we have this training data here, we can say. If we talk about ML, then this is the training data for us. Or I can say create training data. How we are creating? ST. What is happening today? Okay, ST RT plus 1 plus discounted factor RT plus 2. Let us take the rewards here. ST RT plus 2 RT plus 3 for the state ST plus 1. Basically, this let us take the create this data point and use it for the training. Or alternatively, what can be done? ST RT plus 1 plus gamma V bar ST plus 1 theta whole. Just we are substituting the value here, RT plus 2 plus gamma. Instead of writing both these, we are doing estimate of the value function ST plus 2 and theta. But here, if we'll think, in the previous one, the target function was a stationary one. We were saying that this is the target function which we want to achieve. And this is the, wait, let me rename the name here. Basically, what we were saying that this is the target function, it is stationary, means it will not change, and we have to achieve, like we have to go to this target function. We have to achieve this target function, we can say. Now, what we are saying is that this is the basically, what we are saying now is, if we look at deeply, what we are doing is S3 RT plus 1 gamma V. We had ST plus 1 theta old. Now the theta value will be changed after the iteration, after we'll update it, which means that my target value is not now stationary, it is non-stationary in nature. As updated theta, we update the theta value, and what we are getting is ST RT plus 1 plus gamma V ST plus 1 theta of mu. So the target is non-stationary in nature, which means that I am here chasing the moving target, which is obviously not possible if we are like chasing the moving target. But still, it works. It has been proven that it works in many cases here. You can write it as delta E theta T plus 1 theta T. If we are updating it, let us talk about the update rule of the theta T plus alpha into the error. If I talk about the error, RT plus 1 plus gamma ST plus theta minus V hat of ST. Just I have substituted the value of the error here. Now let us move it to the linear parameterization, which I told that we'll discuss in detail. If I talk about the states, basically some states S is going to be represented by attributes or features, as we have discussed earlier also. What is this? In brief only, we discussed that what is linear parameterization. Now what I'm doing is, I'm having the state S, which I'm saying that it is represented by some attributes or the features, which I can say it as phi1 of S, p1 of p2 of S, and so on. Suppose let us take it as k features here. Some k features. These features can be anything. And suppose if I talk about robotic task example, what are the features which we can take? I can say that in robotic task, joint angle 1 can be the feature, angle 2 can be the feature. As such, the features can be anything. Or if I talk about the grid world, then what can be the features? X, Y coordinate. If we talk about backgammon game, as the professor also told us that these features are not revealed yet, but we have total 192 features here in this backgammon game. Okay, let's take an example of grid world only. As I told that in the grid world, let us have the features like X coordinate, Y coordinate. What other possibility can be there to have the features? How many obstacles are there? If I'm in a particular state, like if I'm in a particular state in the grid world, then how many obstacles are up, three, up, left, right, down? So I can say, let us draw the grid world and see first. Wait a second. Let us have this grid world. Or let us have this grid world. Suppose we are standing here. This is an obstacle. This is an obstacle. And this is the obstacle. Suppose the coordinates are 2, 2. I can say that features 2, 2, I am standing, X coordinate and Y coordinate is 2, 2, suppose. So I can say that I am in 2, 2 basically. Or 1, 2, 3, 4, 5 basically. X coordinate is 5, 2, suppose. What about Y, other kind? What I told you that we can represent the grid world as X, Y coordinates. I also told you that we can also represent by the other type of features, which are how many obstacles are there. If I talk about the up thing, up to the plus, like there is no obstacle. I can say 0. If I see the right, there is an obstacle. Down, there is an obstacle. Left, there is no obstacle. So I can represent it like that also. Basically, what does it mean? What I want to say, I can take any problem and think different ways to encode it. The way I have done it in the grid world. I can take in the grid world the coordinates. I can take the obstacle. This is just a toy example which I'm saying. So I can take any problem and can think of different ways to encode. What is the encoding I should be using? It depends. I'll say there is a no right option or answer. It depends what problem you are working on or what problem domain is basically. That is how we'll import. What are mathematical desirable qualities? I can say linear regression. What is linear regression? My features should be linearly independent, I can say. I have S1, S2 till Sm, suppose. Phi 1, phi 2, phi k. Suppose it is of S1 only. There should be, the vector, it should be linearly independent. Question comes into mind, if I take a regression tree, suppose they are not linearly independent. Then what? If my features are not linearly independent, if in the regression tree we are splitting, it doesn't matter. Because what we'll have the redundant one. There'll be, we can say, some additional work here. It will not influence that much about stability and everything, because they'll mostly, I can say, they both are dependent. Which one to choose, it will be a redundant one. If I talk about what is this P of S? Ps, I can say it as whole vector phi evaluated at state S. If I talk about phi1, then it's the first column here, like this. Now, what is the dimension of Ps? What is the dimension of Ps? As we have seen, I said you, what is Ps? Whole vector phi evaluated at state S. Phi1, Phi2, Phi3 till phi k. Phi k, I can say. So, what is the dimension? K. And it is okay that it is K. Now, what is the dimension of phi1? I told you that it is a column wise, like we have to evaluate. And suppose there are m columns here, m. So I'll say that the dimension of phi1 is basically m here. I can write my Vs theta, the estimate of like Vs theta, as theta transpose into phi of S here. Phi of S is whole vector phi evaluated at state S. Now for linear parameterizer, or I can say simply for linear case, I can update the value of theta as taking the gradient and just updating the, we are taking the gradient of v hat of s, like estimate of v, basically estimate of the value function, and just adding this. Or I can write this whole equation as theta t plus alpha var delta t for whole of that delta of like phi of s of t. As 1 hour is over, let's take 10 minutes break and we continue the lecture. let us proceed now to state aggregation method or so. So we have done today also, we have done, and from the starting only we are studying about the lookup tables. Just a second. I think I forgot to share my screen. So lookup table. So sorry for the interruption. Maybe this pen is not working. Wait a second. If I talk about the lookup table is basically also a linear function approximator, a kind of a linear function approximator. And if I talk about this phi of s, which we have represented, I can say that phi of s is an indicator of this function approximator here. I hope so. You got this phi of s as well. What is the phi of s here? Now suppose that we have very, very large state space. Like we have millions of states. And so we have a very, very large state space. Assuming that the states are very large, obviously, if we think about lookup table, that I want to make a lookup table, the lookup table will be million square. I can say the length of that lookup table will be, it will be very tough. First of all, it is taking so much of memory. The second thing is, if it is continuous state, then it is difficult for us. The third thing is that going to millions of states, and that also many times, not only once, to calculate the value function, it is also a very tedious task. So what we came up with as a function approximator. Suppose that if I am having a grid, a large grid, and I'm saying that like of a 10 grid, like 10 grid world, I'll take out of these million grids, the closest 10, all the states will have the same value for me. Same value. What I'm trying to do here is, I'm trying to reduce my K. So that I shouldn't visit every K. I told you what is K here. S1, S2, this is phi1, phi1, phi2 till phi K. So I shouldn't go to every K. I shouldn't go to like this millions of states here. I shouldn't make this lookup table about million square basically. So I'm trying to reduce this K by saying that the 10 states which are close to each other, they'll have the same value. Or I can say 100 of the states which are having the they'll have the same value. Let us say that I'm having this grid. I'm having this grid This is the grade here. Now what I'm saying is, let me take another color so that I can, what I'm saying is, these four states, they'll have the same value. These four states, these four states, these four states, second, these four states, these, this, they'll have the same value, I'm saying. This is basically what I mean by this. I'm trying to reduce the K. I am trying to do the approximation here. So how many were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 30. 30 indicator function were there earlier. Now I have reduced it to 1, 2, 3, 4, 5, 6, 7, 8, 9. By doing the approximation, by saying that this is the like these are like group of the states, they'll have the same indicator function. This method basically is called as state aggregation function. To know what has happened today. So much of issues. So this method is called a state aggregation function, that we are trying to approximate this grid world, like by saying these four squares, they are equal. Now this was just an example of this grid world. Now suppose of the continuous states, if I'm saying. If I'll say of the continuous states, suppose are represented by this circle. Wait a second. Suppose they're represented by circle. I can say that some of the states will be left. Some of the states obviously will not be covered by these indicator function. Let us try to overlap it so that everything should be covered. So what I'm doing here is overlapping. Now, can I say that one state is having more than one indicator function? Earlier, when we see that, is there any problem in the grid world? What we were saying that only one, like for this four of the states, they're having one indicator function. Here, what we are seeing is one state is having more than one indicator function as they are overlapping. There is an overlap. Is there a problem in overlap? Due to the overlap, two indicator function or more than two indicator functions are used here. If we think two indicator functions are not a problem, it is good, it is better, so that we can generalize it more. How we are generalizing? We are basically taking the average of both of them. Basically, what is it if it is overlapping? What does it mean if it is if I'll take this is overlapping with this and this will be the average of both of the indicator function. So more the indicator function, I can say more is the generalization. It will not depend on one only. What I mean is, let me take the grid example and compare it with this overlapping case. What I mean, if I talk about the grids here, I was saying that this grid is having one indicator function and this grid is having another indicator function. Though these both of the grids are together, they are adjacent only, but they are having different indicator function. Is it a right approach? We are saying these states are next to each other, so we are taking one indicator function. These states are next to each other, we are taking one indicator function. What about these two states? They are also next to each other, but we are taking different indicator function. But here we are basically more generalizing it by taking more this is basically average of these indicator function and this other indicator function. So basically we are more generalizing it by overlapping it. What we are assuming is, if we'll think, we are assuming nearness basically. What we are saying is, if the nearness is in the geometric function, then the nearness is in the value function. If they are geographically, or I can say geometrically only, if they are geometrically near, if the nearness is in the geometric space, then nearness is in the value function. Is it always true? That is what we are assuming. No, it's not always the case that the nearness, yes, you are right, Gaurav, that it's not always the case that nearness in the geometric space is nearness is in the value function, we can say. So we'll have some state space embedded in some manifold or something, that where we can say that nearness and distance actually mean nearness in value function. So people try to came up with some basis function here, or some we have this phi1, phi2. What should be the basis function so that this nearness, and then the transforming basis, so that my nearness is nearness in the distance should mean the nearness in value function. If I talk about this case, I have this x coordinate. This is the y coordinate. And this is the goal. If I talk about this, then will like how my value function will look like. It will obviously, it is suppose like it is squeezing like this to the goal. It will slide all the way and it will be the smooth value function. If I talk about this, suppose there is this, and now the point here and the point here, and this is the goal here. The point here and the point here. This is having much larger value because it has to go from here to here. And this is having much smaller value. Can I say that? Yes, because of this wall here. Suppose I'm here, like in this grid only, I am putting this wall here. So because of this wall, this is having the larger value and this is having the smaller value. We can think of some transformation. That is what we are saying. It nearness will always not mean that nearness will be in the value function. So we can make something like embedded like this. This is the same thing going from here to here. This is the same thing. That is what I'm doing. Let's move forward. We have done about this thing, this overlapping. What is this called? Any idea? I think there is some message in the chat. The states near the goal will have higher value. Yes. Yes, coarse coding. You're right, Gaurav. It is called basically the coarse coding. What is the problem with the coarse coding? Any idea? Yes, any idea? What is the like a problem with the coarse coding which we are doing is? Indicator function changes for each state. Okay, if you are saying that indicator function changes for each state, or we can say if there are two indicator functions, then it is a good thing. If we are having more than two indicator function, it is a good thing, na? That it will be more generalized. Okay, you're saying indicator function changes for each state. Okay, yes. So sorry, I thought that you are saying that we have more than one indicator function. Yes, indicator function changes for each state. That indicator function is non-uniform. Very good. Got confused. Indicator function is non-uniform, or we can say number of bits represented for the state is non-uniform. So that is why the indicator function changes for the each state. That is what you said. That is why we came up with tile coding. Tile coding is we'll have this grid. Suppose if I talk about simply this tile coding only, obviously so sorry. got interrupted because of the network issues. Let me connect it again. So it is same as state aggregation. Okay, simple thing. Why it is same as state aggregation? I have just answered it now only, just to have that interaction. Why, if I make this simple tile thing, why it is same as state aggregation? Any idea? Can you unmute yourself or write in the chat? Yes. One indicator function I can say. So that is why it is same as state aggregation function. If I'll try to aggregate the states here, like this is one and like this is one. Yes, we are using one indicator function. Yes. If I say we are using multiple tiles, this is basically what is called as tile encoding. We are using, like, mostly we use 4 to 7 tiles here for more good approximation. What it will say that what we are having here is we are having multiple tiles here. If I am having, this is basically a tile and this is tile link. The number of tile, like we are having here 2 tilings here, and the number of grades which I have made, that is equal to the number of tiles here. And any state here will have 2 of the indicator function. Why I'm saying 2 indicator functions? Any idea? I told you any state here will have 2 indicator function. Why? Yes, why we are having 2 indicator function for this one, for this specific one. I'm not talking about tile coding overall. For this example, why I am saying any state will have 2 indicator functions. Each state can be represented combination of 2 tiles. Yes, and we are having here 2 tiling here. So that is why that I'm saying that any state will have 2 of the indicator functions. One from the blue one and one from the black one. Now, what is the difference between this force coding and this tiling one? Yes. What is the difference between tile coding and force coding now? Is tile coding better or is force coding better? It is more systematic and uniform. Yes. So it is more systematic now, as you told that where the number of indicator functions were different for every state. Now the indicator functions are same as the tiling here, or like if we have 2 tilings, so we can say that we have the 2 indicator function here. So it is more systematic. Mostly we are doing in the practical scenarios 4 to 7 tiling to get the better performance. And talking about tile coding more, it is basically used in CMAC. Professor has also told you cellular mode activator controller, the model of cerebellum. How do we decide the number of tiles? Number of states. Now, can you relate? Yes. Is there any combination between number of states and number of tiles? Come on. You're asking me, how do we decide the number of tiles? What I'm asking you, is there any relationship between the number of states and number of tiles? Yes or no? No. Are you sure? Normal grid example. Or tic-tac-toe. How many number of states are there? Okay. Up, down, left. Okay. If I talk about this number of states and number of tiles, okay, we are not having. Okay. No, like it's random only. Whatever number of tiles you want. Or you can say how much you want to extend a problem. How much, basically, how big is your problem? It depends on your problem only, that how many number of tiles you'll have. Okay, domain knowledge would help them. Yes. Yes. Okay, let's proceed. Let us go to the other topic, that is LSTD. What is the full form of LSTD? Least square, yes, least square temporal difference. If I talk about MSE, mean square error, what we have, we have one approximate value function, one true value function, and what we're trying to achieve is how close is that approximate and true value function. How close is that? And we are doing with the help of MSE sometimes. This is one of the way that we are doing. What we are doing here, we are basically, as we have done only, that we have a state, we are mapping it to phi of s, the features. Assume that I have n states, basically, which means v pi belongs to r of n and phi belongs to, suppose I have k features, then k and k is very less than n. This is suppose might be the true value. It's creating so much of problem. It is sitting in some other space, so I can project it here. Or what I can say is, I can approximate what does it mean? Maybe because of this one you can't get to know. Any idea what I have made? Let's discuss first. Yes. Can you unmute or write in the chat what is it? Okay. You can write in the chat. What is it? Yes. Our VPI is n-dimensional state space, and we want to find an approximate solution in k-dimensional space. Very good. That is what we are trying to do here. I think you got the understanding of that n state space we are having for the VPI residing in Rn states, where each I can say where each coordinate is corresponding to the value of the respective states, and we are also saying that k is much lesser than n, and this is the closest projection to the plane, basically, these stars. I can say it as, now we are basically converging as you have written in the chat also. We want to find an approximate solution in k-dimensional space. Now we are basically converging into V star, which is basically closed, or we can say that is a bounded distance from the optimal one, V optimal one. Now, why this is happening? Ideally, we are having V V optimal one, or I'll say this one, V optimal one. Why we are not converging to V optimal one? Any idea why you are saying that we are going to an approximate one? Why we are not converging to an optimal one? Yes. We have the optimal one. Why we are not converging to optimal one? Why you are saying that we want to find an approximate solution? Why not the optimal solution? And remember from the lecture, there is a lot of variance and we cannot converge to V pi of optimal. Why there is a variance? Because it is not stationary. There is a variance, it is not stationary. Yes, got it. Yes. It is not stationary, it is changing basically. And we are basically doing the bootstrapping thing. And we end up with this approximate one. We don't know its value, the optimal one. And we end up with the doing the we are doing bootstrapping. We end up in bootstrapping, and we end up with this approximate one because of this non-stationary nature. So how we are proceeding is, we start with some V naught, some kind of approximation we are doing on this V naught, and we got V1. We're doing the one more thing. We are also doing the projection here. This is, suppose I'm taking some kind of approximation. And the projection is also done because V naught, we are going to V1 and then projecting it back. This is called V1 bar, going to V1 and then projecting it back. So the projection is also done. We'll continue it until we'll reach some, if I'm starting from V naught, I have to reach some approximate V1, which is bounded distance from the optimal V basically. That is what we are trying to do it. If we talk about the regression thing, the normal regression. We have this inputs and this y as output. if we talk here in this context, we have the features as P1 of S till phi k of S or phi k of S and value function. Do I know this V of S? Do I know? No, we don't know this target. So let us say this V of S is equal to the features which we have taken phi t of S into the parameter theta here. Input is in the form of phi, basically output. What we are saying, phi times this. Output is like phi times the theta here, basically. If we see this, what we are trying to say here is the projection t pi, this one equation, the v pi is equal to v pi. This fixed point solution. What do you mean by fixed point solution? Any idea? My previous lectures I have told, maybe if you have attended. What is fixed point? Iteration, fixed point solution. Yeah, I have something which you can understand. A better example, maybe. Any idea what is fixed point? We have, I think, value do not change on iteration. I was going to give you a simple example, but you know about it. That if you go on doing these iterations multiple of time, a time will come then these values will not change. It will be stable after going to the like 1, 2, 3, 4 till 100, and then we came to 101 iteration. It will be constant. It will not change. The values will remain the same here. So this is basically the fixed point solution. If we talk about this P pi, the approximation, we take it as R plus gamma of P pi. Now, how my projection will look like is this is just the projection thing. If I'll talk about same about Q pi, we'll discuss more. Wait a second. This is about Q pi. Now, what is my V pi? Phi transpose of S, or I can say phi to theta pi. Just substituted the values in this equation. Taking other side. And it is the least square solution which we got from it. Don't worry, I'll discuss this in more detail in the next class. Let us first revise what we have done today in today's lecture. Let's see. We'll discuss these last things because I don't want to hurry up. Wait a second. We talked about the lookup tables here, that how lookup tables representation, like what is the like this was just an example that how we are making the lookup tables, the state action. We are having a particular state and what action should be performed, this policy which is it is telling me, and we are making the lookup table of it. Now, if we have millions of states, so obviously there is a difficulty because it will take so much of memory and it will be computationally intensive. Second limitation we have covered is that if we are having the continuous states, to make up a lookup table is obviously a very tedious task. Then the next thing we learned that if it is supposed that it is not computationally intensive and we are not taking a continuous states, we are taking a discrete states, then what? Though we are not taking, we are having so much of memory so that we can store the millions of states, but to find the value function, we have to visit each state multiple of times, which will obviously itself a tedious task. Though we have that storage, but to find a value function, reaching one state one time is also not enough. And if we are having million states, reaching million states one time is also very tedious, and reaching it multiple times, it's obviously a tedious task. So that were the limitations of the lookup table. Then we went to the parameterized representation. We said that, okay, we come up with the parameterized representation, but we said that parameterized representation also come up with some cost. What cost? Suppose we are making it very complex in nature, and we want that the loss should not be there. Any loss should not be there. The number of parameters, we are saying that obviously if no loss is there, then we are saying that the number of parameters is equal to the number of states. We are going to each and every state in the lookup table because we want to represent every value function. Then what is the benefit of this parameterized representation? No benefit. Then it is same as the lookup table. We are going to every state. We are making parameterized representation very complex to represent every value function. No, there is no benefit of having this parameterized representation. So we have to accept this approximation. We shouldn't run behind this optimal value function in order to it. Obviously, it will be computationally very heavy. So we came up with some function approximation where we are having the true value function. We are approximating some set of parameters. Now, what should be the criteria? First thing we learned about, okay, this was this. First stage, we said that how output is going to depend on theta, or we can say how the parameter theta is influencing or is affecting this estimation of value function. The second thing, am I not going so fast? Are you getting it? Should I proceed? I think I'm speaking. It's fine, I'm getting it. Okay. And the second thing which we got is the second stage is error measure. What is error measure? That how far is the true value from the estimate value. And the main thing which we learned about the error measure is that it shouldn't depend on the choice of the parameters. If it will depend on the choice of the parameters, we can say that if we are comparing two choices, like two choice of parameterization, then obviously there'll be no fair criteria to choose the parameterization, the choice of parameterization. Maybe it can depend upon the choice of the parameters which are using basically. So the function approximators shouldn't depend on the choice of the parameters here, so that as per to have the fair choice between them. What we are doing, find the family of the, first of all, we are finding the family of the function, neural network or decision tree, figure out what is the error measure, then how my theta will give me the good approximation, how it will give me good functional approximation, how it will depend on that. Then we talked about this mean square error, how this 1 by n, this is giving the equal weightage, but I don't want that every state should have the equal weightage. Then we talk about some steady state distribution, d pi. Then I gave you some example of the networks or only the CSMA thing, that what is steady state, that if I talk about DTMC, that is discrete time Markov chain, the number of times I am basically, what is pi here, steady state here, If I am running it multiple of times, reaching to infinity, if I'm running it multiple of times, how much time I'll stay at a particular state, that will be pi of 1. How much time I'll stay at 1? Or if I'm talking about discrete time Markov chain, how many times I'll come up to one state. So that is pi 1. Pi 2 is how much times I'll come to 2, basically. If I told you of an example, I think I erased it. If I'm running it, suppose 1, 2, 1, 2, 3, 4, 5, 6, I reached here again. Then 2 out of 6 times I have gone to one state. This is just a simple but we have to run it many times as per to calculate the value of the steady state distribution until it goes to the stationary. Then we talked about regression, and we talked about that how the target is here non-stationary, so it is difficult here. Then we went to linear parameterization. Then we talk about that we can have like grid world only. We took that example that like how we are having these coordinates. I can take any problem and how I can import them. That is what the main motive of this grid world was. Then we talked about the linear independent, and we said that in regression tree how it doesn't affect to take that. Then how we are reducing it by taking the states. We are reducing it by taking the state aggregation. Then we went to this tile example, uh, transforming basis, coarse coding, tile coding. Then we came to LSCD, which we haven't completed till now, which we'll discuss in the next lecture again. Any doubts? Any doubts? Okay, thank you then. Thank you, class.